Guys, I want to show you a new integration technique today, and this one's called integration by parts. This undoes product rule. So U substitution is what we can work backwards on when the chain rule was used for a derivative. Integration by parts is what we work backwards on when product rule was used to do a derivative. So there's kind of a strange little formula that you use for integration by parts, and I'm not a real big proof person. I'm not a professor who shows you proofs of everything, but I think it's kind of cool to show you where this little integration by parts formula came from. It's pretty easy to follow. You don't have to write anything. So you all know that when you do a derivative on two functions that are being multiplied together, you have to do product rule. So you have to go 1 d2 plus 2 d1, right? So in order to do this, you get two terms. All right. So here's what I want you to do. This is the derivative of this. Therefore, if we integrate all of this, right, we should get those two original functions that were being multiplied together, right? So this is just showing you a derivative, and this is just showing you the backwards progress. Okay, so I've got my integral of all that is equal to f times g. Now, you all know that when you have an integral and you're integrating two separate terms, you can split your integral into two separate integrals. So we can do the integral of this piece with a dx on it, plus we can do the integral of this piece with a dx on it. That's all it was done. And then for the last step, I can say that the antiderivative of just this piece right here, some function times the derivative of what appears to be another function, equals, subtract this from both sides, equals the two originals minus the antiderivative of this original and this derivative. So what we're going to do is we're going to see a function, and we're going to say, you know what, this looks like this might be some original function, and this looks like it could be the derivative of something else. We're going to identify this is the original, this is the derivative of something else, and then we're going to set it up like this. This will be easy to take the integral of. This won't be. Okay? So, that's where it comes from. Let me use simpler terms. U's and V's, ready? We're going to attempt an integral of a function and what appears to be the derivative of another function. To do that, we're going to take this original times this original minus this integral. This integral is going to be doable. Whereas this integral, just with a straight up basic integration, was not doable. Okay? So what we're going to do, we're going to look at an integral and we're going to try to think, you know what, I could identify this as the original function, and I could identify this as maybe the derivative of something. And we're going to set it up like that. Let's try it. Integration by parts. And we've got steps to help us do that. We're gonna pick a U. Pick the one that you think is the original. We're gonna choose a derivative. Which piece do you think looks like could be the derivative of something? We're gonna call it dv. And then we're gonna make this little rectangle out of it. We've written down our U. We're gonna find the derivative of U. We've written down our dv, and we're gonna integrate that. So let me just try one and see how it goes. Okay. So I'm going to say I've got two things being multiplied together. I have an x and I have a sine x. So I'm going to pick a u. I'm going to let u be my x. And then step 2, I need to pick a dv. So basically, whatever I choose for x, everything else that's left has to be my dv. So, okay, we'll say that's dv. And I'm going to turn this into a little rectangle here. So I put u up here, picked u as x, everything else became dv. Now I'm going to fill in the rest of my rectangle. I'm going to do the derivative on u. So I'm going to say that du is equal to 1 dx. Whatever you have for dv should be easy to integrate. So if this is the derivative of v, what would v have been? Let's see, derivative of cosine is sine. I think it would have been negative cosine. Right? So I finished out the rectangle. I've got my originals up here, my derivatives down here. I started with this one and this one. Once I have that little rectangle filled out, here's what I'm going to do. We're going to write, we picked an original, we picked a derivative. Here's what we're going to write. Original times original minus the integral of this original times this derivative. So uv minus the integral of v du. You're going to have to memorize that. U times v minus the integral of v du. Ready? I don't know if I can color code this or not. U times v minus the integral of v du. Original times original minus the integral of v du. There's a lot of negatives in there. You might want to simplify first. So x cosine x, maybe, I don't know, maybe plus. So negative x cosine x plus. The antiderivative of cosine is sine. And it's okay for you to wait until you do your very last integral to put your plus c on here. Okay? Now, when choosing a u, this can get kind of complicated. So when choosing a u, it's nice to choose a u that by doing a derivative, or maybe more than one, by doing a derivative, it goes away. So whenever I have like an x or an x squared or a 2x or something like that, I like to let that be my u, because when I do a derivative on that, I can get my x to go away. So whenever it's time to go u times v minus the integral of v du, I don't have to throw another x back into my integral. Because that was the problem here, right? X by itself is easy to integrate. Sine x by itself is easy to integrate. You throw them both being multiplied together in the same integral, that's nearly impossible without using integration by parts. So that's what I typically try to do if there's one of these available, which there's not always. Check this one out. pick a u, everything else becomes dv. There's not much to choose from. Maybe I'll let this be u, which means everything else has to be dv. Finish out the rectangle. If this is u, what's du? If this is dv, if dv is 1 dx, what was v? V had to just be plain x, right? Because the derivative of this is 1 dx. Okay, let's see how it worked. Let's go uv minus the integral of v du. u v minus the integral of v du. Oh my goodness, that's cool. And sometimes you just gotta, like I wasn't sure what to do, sometimes you gotta just try something, see if it works. If it doesn't, start over. All right, next one. Pick a u, pick a dv. I just said a lot of times I'll try to make u my x, or x squared, or something like that. So let's try it. Let's let u be t squared, so then everything else becomes dv. U is equal to t squared, dv equals e to the t dt. So the derivative of u is 2t dt. And if the derivative of v is e to the t, that means that the original v had to be e to the t. Okay, here we go. U times v minus the integral of v du. Remember, when this happens, hopefully we get an integral that we can now do an antiderivative on, but I still can't. If it were just e to the t, it'd be fine, it'd be an easy derivative. If it were just 2t, it'd be fine, it'd be an easy derivative, but not both of them multiplied together. But notice, I think you can see what's going to happen here. Yes, I chose this to be t squared, but the t didn't go away. Well, not on our first round. I think if we do one more round of this, we can get that t to go away when we do another derivative. So I think what I'm going to do is maybe, I don't know what would be best. I might just pull this 2 out to get it out of the way. I don't know. It might be extra writing. Who knows? T squared e to the t minus 2 times e to the t times t dt. We'll see. So we're fine with this. We don't need to fold that anymore. Integration by parts. Pick a u, pick a dv. So again, I'm going to go with t for my u. U. Thus, dv is everything left inside the integral. E to the t dt. Finish it off. Du is equal to 1 dt, and v would have to be e to the t. And let me just make sure that I have given myself enough room. Okay, this part stays the same. I'm just going to copy it. Minus 2 parentheses. Ready? So in order to evaluate this integral, I'm going to go uv minus the integral of v du. U v minus the integral of v du. Aha. That's doable. Right? So keep in mind all of, oh dang, that's not what I wanted to do. All of this, just this integral right here, is represented right here. Okay. Let's see what we can do. We got t squared e to the t minus 2t e to the t plus 2e to the t plus c. Or if you see that everything has an e to the t, you could certainly factor it out. And if you do, you get a cute little polynomial there, but you don't have to. Either way is fine. So that one took 2 rounds of integration by parts. All right, last one. This one's a fun one. Again, I always try. So 2 things you gotta be careful of. When you're picking a u, my first choice is always like some power expression. But also you gotta be careful, because when you pick a u and therefore whatever's left has to be dv, your expression for dv has to be easily antiderivatable. Like, you need to easily be able to do an antiderivative on that. So, number 4. Looks like pretty much anything would work. Like, u could be e to the x, because I could do a derivative on that, which means dv would be sine x. I can do an antiderivative on that. I could also swap them. U could be sine x. I can do a derivative on it. dv could be e. I can do, Okay. Let's just go with u is equal to e to the x, and sine x is everything that's left. So, du is equal to e to the x, and v let's see, the derivative of cosine is negative sine. Derivative of cosine is negative sine. There we go. Okay. Let's see what happens. We got u v minus the integral of v du. Well, that didn't get us anywhere. I'm like, it's similar to what I started with. Let's clean that up a little bit. Just cleaned it up a little bit, got rid of some negatives, stuff like that. Oh, I don't know. Let's try it again. So du is equal to, I'm in the way, e to the x, and v is equal to sin x. All right, let's see what happens. All right, so everything that's in black is going to stay the same. So I got negative e to the x cosine x plus. Now, this integral, I'm going to use uv minus v du. u v v du. Sorry, I forgot that part. Du was e to the x dx. So in my integral, I'm going to need this and this. I'm going to get a little creative, though, on how I write it. Oh, and I don't know if you noticed this or not. I didn't until just now. There was supposed to be an original problem. We're supposed to be evaluating an integral. Okay, that was supposed to be an integral. You can see that I'm right back to where I started. So I've done 2 rounds of integration by parts. And yes, I got some pieces out of there, which was kind of nice. But I'm right back to where I started. Which, to most of you, you might be thinking like, oh crap, we're right back to where I started. But think about this. Here's the original problem. Let me write the original problem. The original problem is do the integral of e to the x times sine x dx. Now, what have I gotten as an answer to that so far? What have I gotten as an answer to that so far? Well, so far, I just copied and pasted. I copied this line and pasted it down here. So far, that's what I've gotten. So this is what I need the answer to. The integral to this is equal to blah, 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 blah. How about if I add this integral to both sides? Oh my goodness, what do I get? This integral plus the one that looks just like it means I have two of those integrals. So I've got 2 integral e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. You want the answer to this? Divide by 2. Divide by 2. Divide by 2. The answer to this original problem, I know you're tired of writing it, but we're almost there. The answer to that original problem is, and you can even clean it up a little bit. You could factor out an e to the x and swap the sine and the cosine. You can factor out e to the x, swap the sine and cosine, so you just have a minus sign. That's not too bad. All over 2. I know, that was a lot of writing, but that was kind of cool how we did 2 rounds of integration by parts. We recognized, well, crap, I'm right back where I started, but hey, maybe being right back where I started isn't such a bad thing. Anyway, I thought that was kind of fun. Get comfortable doing integration by parts, and then tomorrow we'll do a little bit more with that and maybe like a few tricks or shortcuts here and there. Maybe.